Well, so I mentioned these categories, and I showed you that you compose wires. But it's a little bit too simple. So we need another way of composing things, which is like this, like doing it in parallel. And so there is actually, well, there's a very old tool that comes from the demo scene. I don't know, actually from the German demo scene even, from Farbrausch. It's called Werkzeug, which uses this idea of building graphs or processing pipelines. So you think of something flowing from top to bottom, and when I connect these two boxes together, I now made a graph where this thing, yeah, it's but it flows like now nothing flows, and now this thing flows into this thing, and now they flow into that. So you draw a wire when two things are adjacent like this, and you don't draw them here. So this is a very, actually very nice tool to build from small parts very quickly, very creatively, pieces of code. And apparently I need to do something. Sorry. Oh, I'm starting a timer, that's why. But so we made a tool to, or wait, hold on a second, I was a second. So that's an old tool, that's a demo tool, and that doesn't necessarily use category theory, but it's pretty close actually. So I've been sort of staring at these kind of modular editors for a very long time, and then I discovered some things in mathematics like algebra, and like, hey, this is kind of neat. And at some point there was this boxes and wires thing. In fact, it was actually David's paper was one of the things, the wiring opera, that really got me very happy on this. And the other stuff is from, what's his name? Roger Penrose. So this tensor calculus paper. It's very, very, very old paper, but it has these interesting pictures in it. And I was like, what's this? What's this? Mathematics with pictures? Very interesting. So after thinking about this for a while, we both Jules and me kind of realized the same thing, that there's actually, you can sort of categorify this Werkzeug tool. So let's wake it up. So this is our version of the German Werkzeug tool, and this builds morphisms in a monoidal category. And now you see the wires. So this is tiles of, this is a map. So this is like the wire in my small category example. These are the types. So this is where typedevs lives. And at some point we're going to fill these boxes in, and you'll see a demo of this after our break. And this almost works like an image. So if you see here a number of pixel values, so you can think of this as, where's my mouse? Pixel colors. I'm going to make it very big. So you see here that I have 2, 2, 2, 2, 2, 2. So that's this region over here. I can put the cursor here. And like any serious tool, it has keyboard control. So I can change the size of this thing, because otherwise you're not going to work with this. So you really think of this as, how do we make Emacs for string diagrams or something? Or VI, or Spacemacs, or edit.com, or whatever is your favorite thing. We're actually going to use Visual Studio Code, but and you see here that there's a type checker that tells you what's the boundary of this box, B, B, B. So I have 3 B wires going in, and I have an A, C, D wire going out. And there's 2 ways to render it. So you actually, the wires don't really matter, but you see the boundaries are these dots. And then both me and Jules, we had the same idea of how can you actually turn this into this, which is how you represent this morphism in this monoidal category, really as a tree. It's just a tree, where each branch of the tree has this either do it in parallel or do one after the other label. So that's what this tree expresses here. And you see that as I move my cursor around, the highlight in the tree follows the cursor. And if I make the cursor bigger, you see that I'm selecting 2 things. So I'm doing 4 and 6 in parallel. That's what this says. And then I'm composing this. So after doing 4 and 6 in parallel, I'm going to do 5. And you see that 4 and 6, here the shape of 4 and 6 is described. So it says 4 is a box with 1 B input wire and a CC output wire, 2. And 6 is here. It's just 3 Cs. So Chaos Communication Congress or something like this. And then here we get a box with 5 wires in. I think this should be pretty self-explanatory, kind of, what we're doing here. And by changing this, I can, of course, change the diagram. So I have a box with 1, and I can compose it with 2, and it tells me, oh, actually, this is wrong, because I need 2 Bs. Oh, not like this. I need 3 wires, and then it type checks, and then we maybe put the 3 below it. So, and then check again, what is the type of this whole thing. Right, so this is how we think you work of this, and this is sort of boxes and boxes and boxes, like, you know, monoidomorphism all the way down or something like this. Another maybe important thing to show about this is actually in here. To open the JavaScript console. And that's this part. This is where we actually track the morphism, this thing, as a piece of code. So this is the language agnostic description of this wiring. And these boxes could mean anything. It could mean, which is what Statebox originally is implementing. Well, actually, originally it was relations, but we sort of put that on hold for a while. So now it's state machines, or Petri nets. In each box, there's a Petri net. This is how it starts. This is the 3 ways in which it might end. They go into this other box, so that's one way. Another thing, what you will see after the break, is that you can actually put pieces of game theory in here. This is very, very exciting research that, that just ties into this. It uses the same language, so we can just take this editor, give it a different semantics, and that's what one of the things we did at the summit, and that's what you're going to see after the break. And I don't think I'm going to say much more about this right now. Any questions?